You are watching the 9.7 lesson video on residuals. And in this lesson, we are going to talk about residuals and their graphs and what they are basically used for. We are going to use them to determine if a specific model actually makes sense. So in exercise number 1, we have a skydiver who's jumping from an airplane, and an attached microcomputer is recording the time and speed of the diver for the first 12 seconds of their free fall, and it looks like it's recording it every 2 seconds. For part A, it says using your own technology, let's plot this data. As you can see on my calculator, I have already typed in my data. If you haven't done that, which you probably haven't, just pause the video now and go ahead and type in your data. All right, now that our data is typed in, we are going to add a page, and we want to add the data and statistics. And remember, to add variables to our data, we can either move the mouse and click it, or I think hitting tab is a lot faster. So you can just hit tab, and we want this to be time, our x-axis to be time. Hit tab again, and we want our y-axis to be speed. So now you can see a picture of what is on your paper. It says here, find the equation for the line of best fit. So it's saying line of best fit. That means we have to calculate a linear regression. We could go back and do this on our table page, or we can calculate it right here. I'm going to just do that because it's not asking us to find our correlation coefficient. If it did, then we'd have to go back and figure that out in a different place. So we can analyze our graph, do a regression, and remember it's linear, and we typically do y equals mx plus b. All right, so our equation rounded to the nearest tenth would be y is equal to 6.0x plus 13.1. Now C says, just by looking at the data points, do you think a linear model is a good fit? Well, what do you guys think? Is this a good model? I don't really think so, because it looks more of a curve-like shape. No. The data has a curve. Okay. So now D says, oh, of course, I should have read ahead. Determine the correlation coefficient and round it to the nearest hundredth. So we're going to go back here and do another linear regression all over again. It's okay. We've done it before. We've practiced it a lot. We should know what to do. Okay, so after we hit menu, we want to do some statistics. Oops. Statistics, stat calculations, and we need to do a linear regression. Time is our x. Speed is our y. And there you have it. So let's scroll down to get that correlation coefficient. All right, so the correlation coefficient is, why is this not working? Here we go. So the R is equal to, well, it says round to the nearest hundredth. So 0.9, that would be the second decimal place. So is that going to stay a 3 or bump up to a 4? It becomes 0.94. Okay, so not bad. So it's saying based on the correlation coefficient, characterize the fit as positive or negative and how strong of a fit it is. And, you know, it's 0.94. This is a pretty decent fit. So let's call this a positive correlation. And positive, and let's even call it strong. We know this because it's really close to 1. So maybe we were wrong. Maybe a linear model is best because it has a positive strong correlation. Okay, so we need to graph our line of best fit on a graph page on the calculator and complete this table below. All right, so I'm going to add a new page. We're going to add a graph, and let's pull our line of best fit equation, which is 6.0. I guess I didn't really need to put the 0.0, but whatever. X plus 13.1, and it looks like we need to complete this table of value that we have right here. And you know what? Why don't we round it to the nearest whole number? Let's just add that in there. So round to nearest whole number. You don't get to change questions, but I do, so we're going to do this just so we don't have to keep writing 0.1 every single time. So 0, our y-intercept is 13, and 2, 25, 4, 37, and so on and so forth. All right, so now that our table is completed, moving on to part G, it goes on to tell us how we even calculate a residual of this data. So the residual is the difference between the actual and the predicted. So actual, what you actually got, and what we predicted using our line of best fit. So what we actually need to do here in the table is copy and paste the values that we just wrote right up top. Okay. What we need to do here is take the actual and subtract the predicted. So 0 minus 13, that is going to give us the residual of negative 13. 25 minus 25 is 0. Go ahead, pause the video, and finish that table. Just simple subtraction. So these look a little weird. I wrote all my residual values in purple, and some of them are negative. We actually have one at 0. And remember, these are the differences between that line of best fit and the actual data points. All right, let's move on here. So what we want to actually do now is show this residual on our calculator. We need to go back to our graph here, where we showed all of our data, okay? And we need to follow our study guide, which I have open right up here. So down below here, it tells us what to do. So once we have done all of this, we have to go through all of these steps. Okay, so what you're going to do is you'll hit Menu, then Analyze, and let's hit Residuals. And we want to show the residual plot, not the residual squares. Well, this is weird. Okay, so now our residuals are actually showing this pattern. It almost looks like a quadratic. And usually we might say, oh yeah, this is going to be a quadratic regression, but that's not what we're doing right now. We're looking at a residual plot. So we did part H. Do the residuals show any distinct pattern? Yes. It almost looks like a parabola, or like a negative parabola. And what does this mean? Well, this actually means that our linear model is a bad fit. Anytime that it shows a pattern is a bad residual plot. We want it to be as scattered as possible. Remember, if we were to draw a line through all of our data. Okay, we would want the points to be above, below, above, below, above, below, above, below, you know, scattered. We don't want a ton of them to be below. We don't want a bunch of them to be above, then a bunch of them to be below again. We want it to be as scattered as possible. So patterns are bad when it comes to residual plots. That's one of the most, I think, confusing pieces about a residual plot. Okay, so if we read on, it says, generally, we do not want residuals to fall along a curve or make a distinct pattern. So what that just means to us is that a linear model is not best. We probably need to use either an exponential or quadratic model. But for algebra purposes, we just need to know whether or not a residual plot shows a good model for the data. So is a line of best fit good or bad? If the residual plot makes a pattern, it's a bad fit. If it's scattered, it's a great fit. Okay, so exercise 2 says, after performing analyses on a set of data, Jackie examined the scatter plot of the residual values. And we are trying to find, so which scatter plot indicates the best linear fit for the data. We are looking for no pattern at all. So 1, there's definitely a pattern. 2, I'm thinking that's my right answer, but let's just double check. 3, there's a pattern. 4, there's also some type of a pattern. 3 and 4, we could probably draw some type of a V or a U. So 2 is the best linear fit. The data, or actually let's say the residual plot, does not have a pattern. Okay, and I'm just going to go right back up to the first example that we were looking at, and I just wanted to show you that the line of best fit turns into the x-axis. So it's almost like you take the line of best fit and plop it down, make it the x-axis, and then you can see, okay, so this point right here is this one there. This point right on the line is there. This one above the line is that above. See how this point's a little bit higher than the other one? That's why that one is there too. This one's a little bit closer to the line. That's why it's coming down closer. This one is sitting right on the line, slightly below. Obviously that one is too, and so on and so forth. Okay, so that would just help you to see, if I were to pull this, maybe this looked like, I don't know, if it were a line, maybe it looked like this, and a bunch of scattered points above and below, like that. That would be just an estimate. Okay, exercise 3, we're almost done. So exercise 3 said the residual plots from 2 different sets of bivariate data are graphed below. Explain, using evidence from graph A and graph B, which graph indicates that the model for the data is a good fit. Again, if we're looking for a good fit, we are looking for no pattern. You are right. Graph A is a good model. Because the residual plot does not have any pattern.